All right, so last week we did all the graphs, right? All the graphs of the exponential functions. We did, so we're going to go back to those, okay? We started with number 6, so if you want to jump to 6. Before we did the transformations, we talked about how we simply would just plug in points for these. So this one said f of x equals 1/10 to the x. And then we said we would set up a t-chart. WebAssign gives it to you, but let's just say you were given -2, -1, 0, 1, and 2. And then we would take each of these and plug them in. So 1/10 to the -2, 1/10 to the -1, 1/10 to the 0, 1/10 to the first, and 1/10 to the second. So what's 1/10 to the -2? What happens? What does the negative do? Moves it to the top, so that would be 10 to the second or 100. 1/10 to the negative first. Good, moves it to the top, to the first power. Anything to the 0 power is 1. 1/10 to the first would stay 1/10, and this would be 1/100th. So when we go to graph this, we would plug those in. So -2, 100, 0, 1, or -1, 10, 0, 1, 1 and 1/10, and 2 and 100th would be my coordinate points. So -2, obviously 100 is not on here. It would be way up here. I would just plot it and label it because it's off my graph. -1 is 10. 0 is 1. 1 is 1/10, and 2 is 1/100th. So we're not going to get that accurate, but at least know that it would be really close to your x-axis, which is where the horizontal asymptote is here. Remember, the horizontal asymptote comes into play when there's a vertical shift. If there's no vertical shift, like in this scenario, then my horizontal asymptote is right there at that x equals, or y equals, 0. We talked that we would eventually add on like domain and range here, right? Domain was all real numbers because I can plug in any value for x. Range starts wherever that the horizontal asymptote is, which would be 0, and goes up to positive infinity. If I wanted the y-intercept, it's from the middle point of my graph, or where an x is 0, or you can get it from your t-chart 0, 1. Yeah.
How do you know that it was facing the other way?
It falls as it moves right just because it gets littler. Is that what you mean?
Yeah.
The point values just get littler, but fractions. A fraction raised to an exponent would make it fall as it moves to the right. Okay, then we had 8. Yep. This one is -3 to the x. So I'm going to do the same thing. -2, -1, 0, 1, 2. -3 to the -2. Now that negative is not in the parentheses with it. So what do we do with that negative? Is that -3 times -3? No, it is -3 times 3 to the -2. So the negative in this exponent makes this -1/3 to the second, which makes this -1/9. So the negative that's not in the parentheses is the last thing that gets applied there. So -3 to the -1 would be -1/3, or -1/3. -3 to the 0 would be -1. -3 to the first would be -3. And -3 to the second would be -9. So that negative stays on the front because it's not inside the parentheses. Then we go to graph. -2 and -1/9. -1 and -1/3. 0, -1, 1, -3, and 2, 9. So my horizontal asymptote did not move. There's still no vertical shift here, but what happened is my curve comes underneath it. So it flipped, just think about the reflection there, it flipped over the x-axis because there's a negative on the front. So my domain wouldn't change here. It'd be -infinity to positive infinity, but my range changes here because I'm now going from -infinity up to 0. So because my curve flipped underneath the axis, it would change. The y-intercept still comes from the middle point, 0, -1, and my horizontal asymptote is y equals 0. So the only thing that really changes here, because it's flipped over it, would be that range.
We're going to actually have to know the transformations, like
you're going to plot points. The things you would need to pay attention to are the asymptotes, which is going to happen with that vertical shift. So like nothing has changed right now because there's been no vertical shift. That's the thing you have to pay attention to. Everything else you'll see from your points. But you need to know where to put the horizontal asymptote. So if there's no plus or minus after it, then it's at 0. You may not catch it if there's a vertical and a horizontal shift. You'll see the points, but remember there was that one that they all stayed teeny tiny. Forget, right? So the difference here is this is a shift vertically. This is not. So 12 is going to cause a shift to my horizontal asymptote. It's going to be at 3. But 11 is still at 0. Yeah, you still plot the points the way you plot them. It's just that without having, first of all, it might ask you flat out what's the horizontal asymptote. You're going to have to give it in equation form. Second, sometimes depending on the shifts, you don't get that natural curve. You have to find the curve from the asymptote. So I'm going to do this kind of quicker. I'm just going to do negative 1, 0, and 1. If I plug in negative 1, I get negative 1 minus 2. That's 4 to the negative third, or 1 over 64. Then I'd get 4 to the 0 minus 2. That's 4 to the negative 2. That's 1/16. And then I get 4 to the 1 minus 2, which is 4 to the negative 1, or 1/4. So this is kind of that example of if it's negative 1 and 1/64 and 1/16 and 1, 0, we don't fully catch that curve. You'd have to know that it's curving up. If you want to keep going, you could plug in additional points to the right. Like the left isn't going to help you, but if I plug in 2, 4 to the 2 minus 2 would be 4 to the 0. Now I know I'm at 1. Oh, I already did that one. Oh, no, I didn't. This was 1/4. 2, this should be lower because that should be 1/4. 2 should be 1. So it'd be like that. Okay, if I go one more, I'm going to be at 4. So that's how you can kind of get that natural curve. But you have to know where that asymptote is to either, I would assume, well, we haven't made this one, but I would assume that you're going to get a graph and it's going to ask you for all those parts. Okay, so now I get 4 to the negative x minus 3. Is there a change in my horizontal asymptote? Where is it? Good. It's at negative 3. So horizontal asymptote is at y equals negative 3, and then I could still plug in my points. Again, I'm going to cheat, just do these 3 for now. 4, negative 1 minus 3 would be 4 to the first minus 3, which is 1. 4 to the negative 0 minus 3 would be 4 to the 0, minus 3, or 1 minus 3, which is negative 2. And then 4 to the negative 1 minus 3 is 1/4 minus 3, or negative 2 3/4. So negative 1 and 1, 0, negative 2, 1, negative 2 3/4. Questions on the graphing before we get into one-to-one? So the rest of this section is not graphing. The rest of it takes your exponential functions, and we do something called finding the one-to-one property to solve them. We're good on the graphing? Yeah? Okay. So the one-to-one property works for anywhere that the base is greater than 0 and it's not equal to 1, just like an exponential function, right? It can't be 1 because then it never changes. And to do this, we change the bases to be the same. So if the bases on either side of the equal side are the same, then the exponents can be set equal to each other. So it works both ways. A to the x equals a to the y if and only if x equals y. So this equals each other only if the exponents also equal each other. In these types of problems, there's going to be a variable in the exponent, and we have to work to get the base to be the same, and then we just set the exponents equal to each other. So usually, it's not always possible, but usually when it's possible, we will change the larger base to a power of the smaller. For example, if I had 2 to the x equals 4, I know you know this already, but we could rewrite this using the one-to-one property by making the bases the same. 4 is 2 to what power? 2. So I could rewrite this as 2 to the x equals 2 squared. And then once the bases are the same, I literally set the exponents equal to each other. And my answer would be 2. That's never going to be that easy, but that's the concept, okay? The goal is to change them so they have the same base and then set the exponents equal to each other. We usually do it with a larger, like if you have 3 and 9, obviously you're changing the 9 because you can't change 3 to be something to a power, a 9 to be something to a power. You can, but it gets complicated. And again, remember anything raised to the power of 0 is 1 because you're going to see that sporadically throughout here. All right, so start with 15. Look at your two bases, 9 and 3. Which one's bigger? 9. How do I rewrite 9 so it's a power of 3? Good. 3 squared would equal 3x plus 1. Once the bases are the same, you literally ignore the bases and set the exponents equal to each other. And then solve for x, and I'd get x equals 1. Some of these are so quick and easy to solve, you just have to plug it back in here. Would 3 to the 1 plus 1 would be 3 to the second, which is 9. They're not all going to be that quick to check, but you can check every single one. Okay, go to 16. How do I make them the same base? How do I make 1/2 have a base that's a whole number? Put a negative exponent. So this would be 2 to the negative 1, right? That's the same thing. 1/2 is the same as 2 to the negative 1. Can I raise 2 to a power to get to 8? Yeah, right? It's 2 times 2 times 2. So this would be the same thing as 2 to the third. Now we disregard the bases and we set the exponents equal to each other. Negative 1 times x would be negative x equals 3. Divide or multiply by negative 1, and x would equal negative 3. Yep. Sure. Yeah. You could change, as long as they're the same base, you can make them, yeah. You don't have to, you're saying don't move the 2, move the 8 to the bottom. Yeah, that doesn't matter. As long as they're both the same at the end.
Where did the negative x come from?
Because we had to, in order to make 1/2 become 2, to move it, it becomes a negative exponent. So if it was in the top, you wanted to move it to the bottom, you would do negative exponent. If it's in the bottom, you go to the top, same thing. Okay, 17. So again, I'm going to leave the 2 because that's fine. The 8 becomes 2 to the third equals 2 to the 2x minus 1. My bases are the same, so now I jump just to the exponents. 3 equals 2x minus 1. Add the 1. 4 equals 2x. Divide by 2. And x equals 2. And again, you can plug it back in to check. Good so far. That's basically the entire one-to-one property. They just make it a whole crap ton more complicated sometimes. That's all. All right, look at 18. What could you do?
3 to the negative first, x equals 3 squared.
Good. 3 to the negative, well, to the third, yeah. 3 to the negative 1 raised to the negative x would equal, and this would be 3 to the third. Bases are the same, set your exponents equal to each other. Negative 1 times negative x makes that x. $19, do the same thing. Bring 3 to the top. It'd be 3 to the negative 1 raised to the x. 81 is 3 to what power? Good. Set the exponents equal to each other. Negative x equals 4, so x would equal negative 4. Which one are you going to change in 20? Oh, sorry, go ahead.
Does that mean that number 18 is supposed to be negative 3?
No, because the negative was already in here.
Oh.
So when we brought the negative in, it canceled it out. 20, what are you going to change? The 8, right? So I'm going to leave the 2 by itself. The 8 becomes 2 to the third. Now this is 2 to the third raised to the x minus 6. When we raise a power to a power, you multiply them. So this 3 is going to get distributed to both. So this would be 2 to the x plus 4 equals 2 to the 3x minus 18. So we're raising a power to a power, which is why we multiply. Now the bases are the same, so we disregard the base and just set the exponents equal to each other. Subtract the x. 4 equals 2x minus 18. Add the 18. 22 equals 2x. Divide by 2. And x is 11. And again, you could check it. With extra time, you could plug that back in to check it. To check, I would plug 11 in for both. So I would do 2, 11 plus 4 equals 2. Nope, not 2, sorry, 8. 11 minus 6. So this wouldn't be fun to do without a calculator, but you could. Yeah. Those two numbers would be the same. Yep.
Are we gonna get a
All right, what do I do with 21? Good. 2 to the 3 minus x equals 2 to the 3rd. The bases are the same. Set your exponents equal to each other. Subtract the 3. Negative x equals 0. X would equal 0. That one's an easy one to check, right? Plug 0 in. 2 to the 3rd equals 8. You're done. What do you change on 22? Good. 5 to the 2x plus 1 would equal 5 squared. Set the exponents equal to each other. Subtract the 1. 2x would equal 1, and x would equal 1/2. Go to 23. Now the base is already the same on 23. They're both e's, right? So I'm just going to set the exponents equal to each other. It'd be 4x minus 1 equals 2x. So even though it's an e base, we don't need a calculator because the bases are the same. So I get x equals 1/2. For 24, you have to change both these bases. So 27 is 3 to the 3rd, and then that gets multiplied by the 4x to get the 12x. 9 becomes 3 to the 2nd. That 2 gets distributed to both the x and the 1. So it becomes 2x plus 2. Subtract the 2x, you get 10x equals 2. Divide by 10, and 2/10 is 1/5. For 25, you're changing the left side, so 2 to the 2nd, and then that gets distributed to both here, so that becomes 2x minus 4. This does not get distributed because that is the exponent. Subtract the 2x from here and here, and then subtract the 3, and you should get x equals -7. And then 26, you don't have to move the e to the top. You could keep it in the bottom as long as they are both 1 over e. So that 2 would have to move. That's the problem. So if it was just both 1 over e, then you could keep it. But they are 1 over e and 1 over e to the 2nd. So I brought both to the top. This would have been e to the -1st in the top multiplied by a -x, and that's why it becomes a positive x. And then e to the -2 in the top. That -2 goes to both the x and the +1. Add the 2x, you get 3, and then 3x equals -2, and then divide both sides by 3. Oh, this should be flipped. And it's x equals -2/3. Raise your hand if you got all 3 right. Better than me, because I screwed up the last one. Good job. Okay. Remember, I said they just get a little bit jankier, right? A little bit more complicated. So looking at 27, I've got the square root of 2 to the x plus 4. What's the same thing as the square root as an exponent? How quickly we forgot square roots. Square root is the same thing as 2 to the what? 1/2. Okay? So square root 1/2, cube root 1/3, anything like that, right? The index was on the front. So this is actually 2 to the 1/2 raised to the x plus 4 equals 4 becomes what? 2 squared raised to the x. So now my bases are the same. I have 1/2 x plus 4 equals 2x. You can either distribute the 1/2 or you could get rid of the 1/2 by multiplying everything by 2. You do what you want to do. If you wanted to get rid of it, I could multiply both sides by 2. And I'd get x plus 4 equals 4x. And then subtract the x. 4 equals 3x. Divide by 3. So square roots become 1/2. Like I said, cube root would become 1/3. So if you saw something like that, you could do that as well. Okay, 28, and that is a b. That is 1 over 27 equals b to the negative third. Can you change b to be another number raised to a power? No. So think about how else we could set this up. What does the negative 3 do on the b? 1 over b to the third, right? Can we solve that? How? Go back. Pretend like you don't even know the one-to-one property. I could cross multiply it, right? Or because both in the top are 1, both in the bottom can be set equal to each other, right? You could do that too, just like a equivalent proportion. So this would be b to the third equals 27. And then how do I get rid of a third power? Cube root it. What's the cube root of, ooh, that's so ugly. What's the cube root of 27? 3. And then again, think about it. If you check this, 3 to the negative 3 would be 1 over 3 to the third, which is 1 over 27. Rational exponents are back. So 4 equals r to the 2/3. Think about how you would solve this. How would I get rid of an exponent that's 2/3?
Cube root squared.
Good. Raise it to the reciprocal, which would be 3/2, right? What happens when you square root both sides of an equation? You have to do plus or minus. So when I come over here to do 3 over 2, I have to remember to do plus and minus. So this means plus and minus the square root of 4 cubed. So there's two things happening here. A negative square root of 4 to the third power and a positive square root of 4 to the third power. So because the index slid over to become the square root on the front. Square root of 4 is 2. Negative 2 to the third is negative 8. Square root of 4 is 2. 2 to the third is 8. So that one's tricky because it goes back to your rational exponents. We did those a long time ago. But when you are doing the even root on both sides, because that's a square root, you got to remember to do plus and minus. Still good? Okay, so not yesterday. Friday we talked about e, right? E to the x it's an exponential function, and e is called the natural base. So remember e, I told you it was 2.7, right? It's actually a number that doesn't end. It continues on forever. It is 2.7182818228. Doesn't end, doesn't repeat. It's an irrational number, okay? We approximate it to be 2.7 if we needed to. We can use the graph to graph, like a graphing calculator to graph it if we need to. What we're going to use it for in a minute, you're going to see, is it's part of an equation for interest problems. So the last section or last couple questions in here get into interest problems. How do I earn interest that is either compounded a certain amount of times a year or continuously? So let's say you have money and you put it into a savings account. More likely you put it onto a credit account. That's a lot of times they're talking about credit card accounts, that kind of stuff. And it's accruing money. So if you put it in a savings account, you're earning interest, that's good for you. If you're putting it into a credit card, you're getting charged interest, it's bad for you, okay? But they are both figured out the same way. The formula, if it is being compounded a certain number of times a year, is that P, it's A, which is the account balance, equals P, the principal balance, whatever money you put in there, times 1 plus R over N to the NT. Now the R has to be in decimal format. It will give it to you in percent. You'll have to move it into decimal format. The N is the number of times a year. So if it says it's being compounded monthly, how many times a year is that? If it was quarterly, 4 times a year. If it's weekly, 52 times a year. Daily, 365. Those are all things you have to know because it will change that. how many times it's being compounded. That's your N. And then T, did I say that one yet, is the number of times a year. I mean, sorry, is the time in years. So if it'll say like for 10 years it's being compounded X amount of times, all that information you literally just plug into the formula and then you let your calculator do the work for you, okay? So what? Yeah, there are words in them. They are more numbers than there are words usually, but it's literally one formula, you plug it in, that's it. Ew, like that. That's a lot of words, I guess, if you compare it to a word problem. Yes. It says invest $12,000 at an annual rate of 3% and find the balance after 5 years compounded quarterly. So it is A equals P times 1 plus R over N to the NT.
Do we have to memorize that?
Yep. The A is what I'm going to get out of this answer, okay? The P is how much we put in there. How much did we put in? $12,000. The R is the rate in decimal. So my rate is currently in percent, right? 3% would be what in decimal form? 0.03 or 0.03. Good. N is the number of times of year it's compounded. So what does this say? That's the T. Quarterly is the number of times. So how many times is that a year? 4. And T is the number of years it's in there, which is 5. That's it. Plug it in. So 12,000 times 1 plus 0.03 over N, which is 4, raised to the 4 times 5. And your calculator can do that whole thing in one swoop. 12,000, open the parentheses, 1 plus 0.03 divided by 4. You don't even have to put parentheses around that because it will know. And then the little caret to get the raised to 4 times 5. You should get $13,934. It actually is 209. So we round it because it's money. We round it to the cent, which would be 21 cents. 31, invest $12,000, annual rate of 3, find the monthly balance after 5 years, but this time it's compounded monthly. So everything is the same here except what's my N? Good. So it'd be 12,000 times 1 plus 0.03 over 4, nope, over 12 to the 12 times 5. $13,939.40. Again, rounding to the nearest cent because it's money. If you don't have your calculator with you today, make sure you are practicing this, okay? Because you're going to need to obviously be able to type that into the calculator. The last formula is if it's called being compounded continuously. So this is happening so often like your normal brain cannot figure it out. It's not an N number of times of year. It is happening. And compounded means like if you start off with $100 in account and you get 5%, right? And it's compounded, let's say it's monthly. At the end of the first month, you're going to get 5% on that $100. What would be 5% of $100? $5. So at the end of the month, I have $105, right? You with me so far? If it's compounded, now it's compounding off of the 105. So now I'm not just earning 5% off of 100, I'm earning 5% of 105. So that's what it means by compounded. Does that make sense? So in all of those other scenarios, it's either monthly or it's annually or however many times a year it is. When you're using E, it's happening so frequently that your normal brain would not be able to count how many times it's happening. So E is just the base. It goes there. It's not a big deal. Your calculator has an E button. You literally just hit that. But that's why it's happening. It's happening so often that it wouldn't be you couldn't count how many times a year, okay? So it would be P is still the initial amount times E, which is that function on your calculator, the 2.71 and so on and so forth, times R, or raised to the RT. R is still in decimal, okay, and T is still time in years. So the difference again, and the wording on this would say compounding continuously. The other one would be a certain number of times of year. I call this PERT. That's how it's spelled. Helps me remember how to do it, okay? And they'll look like this. Invest $12,000 at an annual rate of 3%. Find the balance after 5 years compounded continuously. So as soon as you see continuously, that's your PERT, okay? A equals P E to the RT. So my principal balance is again 12,000. My E is E. The annual rate of 3% would be 0.03, and the T in years is 5. Notice that there's no mention of how many times a year. That's the difference between continuously and the others. 12,000. E is above your LN button, 0.03 times 5. So it's $13,942.01. If all the other parts were the same, but you were comparing something that's compounded once a year to continuously, you're going to earn a lot more on continuously because it's constantly updating. If you compare it, so like if I compare this back to the last two, continuously should always be the most amount of money. If you compare it to like being compounded 365 days a year, it's not going to be that big of a difference. It will be a small difference, but continuously compounded should always be the most if everything else stays the same. Yep.
Would you just want us to round it to decimal places?
Yep, just like it's money. Everybody's good? Yes? Okay.